Alright, so in today's video we're going to be talking about salt hydrolysis and going over some basic salt hydrolysis problems. So first I've compiled a bunch of the hydrolysis rules that are necessary for solving these questions. So as I go through the questions I'll be referring back to this list of rules. And then over here I've written some important formulas that you need to know in order to solve these questions. So here I have the Ka and then the Kb here. And then I also have a little formula that talks about the relationship between Kw and Ka and Kb. And you need to use this if, for example, they give you Ka and you want to find Kb, or the other way around. So this formula is really helpful. So let's start with the first few problems. So it's asking us to predict whether the following solutions will be basic, acidic, or neutral. So if we refer back, first, the first step would be to write the dissociation equation. So NaNO3 would dissociate into Na plus ions and NO3 minus. Now what we need to do in order to see if it's acidic or basic is look at the two ions that it's formed. So if we go back to the rules, let's look at Na plus. So this fits into rule number 1, where it says metal ions of group 1 and 2 do not hydrolyze, therefore they produce a neutral solution. So I'm going to go back down and write Na plus is a group 1 metal, therefore it's neutral. Now let's look at NO3 minus. NO3 minus is the conjugate base of HNO3, which we know is a strong acid. So if we go back to the rules, this should be rule number 2, where it says the anion is the conjugate base of a strong acid. It produces a neutral solution. So then this too is going to be neutral. Now if we have two neutral solutions, that means our pH is going to equal 7. So this is neutral. Now let's move on to example B. Just like before, we need to write the dissociation equation. So this is Na plus plus CO3 minus. And then if you want to balance it, we can put a 2 in front. So same as before, Na plus is a group 1. So it's neutral. And CO3 minus is the conjugate base of HCO3, which is a weak acid. So now let's go back to the rules and see if this is acidic or basic or neutral. So if we look here, it's the anion of a weak acid, and here it says it produces a basic solution. So therefore, this one will be basic. So if we have one neutral and one basic, this resulting solution should be basic. Now for example 3, same thing, let's write out the dissociation equation. This has a charge of +3, and this is Cl minus. So Cr3 plus is a ligand actually, because it has a charge, it's a metal ion with a charge of 3 plus or more. So if we go back to our rules, it says ligand in complex ions. So metal ions with +3 charges or greater tend to form acidic solutions. So therefore, chromium, the chromide ion, will form an acidic solution. And then Cl minus, this is the conjugate base of HCl, which is a strong acid. And then going back up, this is going to be rule number 2, so it's going to produce a neutral solution. So if we have one acidic and one neutral, the pH will be acidic. So now example D. This one, same thing. Write up the dissociation equation. So NH4 plus and then Cn minus. So NH4 plus. This is a special case. It's not like the other ones where we have two things that hydrolyze. So both of these will hydrolyze actually. So this is the conjugate acid of NH3. And if we go here, a conjugate acid of a weak base is this one, rule number 4, and it will produce an acidic solution. And then Cn minus is the conjugate base of HCN. So then this should be rule number 3. So it'll produce a basic solution. Okay, so what do we do now? We have one acidic and one basic. Well, now we actually need to use rule number 5, which states that if both of them hydrolyze water, the calculations, we can look at it qualitatively by comparing the Ka values. So let's do that right now. You'll have a Ka chart. So if we look on that, the Ka for NH3 is around 5.56 times 10 to the negative 10. And then the Ka for this one would be, this would be Kb, since it's basic. And this would be 2.51 times 10 to the negative 5. So now we have our values, and all we need to do is see which one is bigger. So which one's bigger here? Well, Kb is greater than Ka, because we know that this is less. So will it be acidic or basic? Well, it says if the Ka for the acidic ion is less than the Kb for the basic ion, the solution will be basic. And that's what we have. Our Kb is greater than Ka, so therefore our pH is greater than 7. So those are all for examples. Now let's move on to some more complicated equations. Or not equations, some more complicated problems. I'm going to quickly erase this actually because it's taking up some space, but you can always replay the video. So calculate the pH value for the following salt solution: a 0.1 mole per decimeter minus cubed solution of potassium cyanide, given that the pKa for hydrocyanic acid is 9.4. So how do we do this? Well, we always start it the same way. We write out our equations. So the KCN will dissociate into K plus and Cn minus. And they also tell us the concentration of this. It's 0.1. And with these questions, we assume that the dissociation goes completely to completion. So that means the concentration of the Cn minus is also 0.1. We can write a second equation where we hydrolyze the Cn minus. So you just add water, use your equilibrium arrow, and this should be HCN plus OH minus. So the next step we need to do is calculate the Ka value, and then that allows us to use the first two equations here. Well, they give us pKa, which is 9.4, and we can use that to find Ka. So pKa equals the negative log of Ka, and Ka equals 10 to the minus pKa. So important that you know your logarithm rules. So then our Ka will be 10 to the minus 9.40, and if we calculate this, you'll get 3.98 times 10 to the negative 10. Now we're not done yet, because if we look here, this is going to make OH. So if you look back to the formula, we have an OH here. So we actually need Kb, but here we have Ka, and this is where we use the formula over here. So this is really simple. Kw equals Ka times Kb. And we know that Kw is always 1 times 10 to the minus 14. And we got the Ka to be this value, so now we can just solve for Kb. And Kb should be 2.51 times 10 to the negative 5. Yeah. So now we're ready to create an ice table. Basically, this ice table is just a way to organize everything so we can come up with the correct formula and plug in the right values. So I'll do the ice table in green. So how this works is you're kind of going to translate this formula down, and then you can also get rid of the H2O because H2O doesn't have a concentration, so you can kind of ignore it. So Cn minus, and then HCN, and OH minus. I'm going to put a line between here just to show that, to differentiate between the products and the reactant side. And then here you're going to write ICE. The I stands for initial concentration. So Cn, as they told us in the question, is 0.1. And then the products are going to be 0 at the start. Our change, we don't know what the change will be, so we're going to just say minus x. And then because these are all equimolar, they're all going to be added by the same amount of x. And then E stands for equilibrium. So it's just going to be that. So initial change equilibrium. And now we can use this to make our formula. So Kb equals HCN over OH minus over Cn minus. And then we can plug in our values. I'm just going to say it right now. For all of the questions that you're going to do, basically, you're going to assume that these top two values are equal to each other. And we can do that because there's something called a 5% rule, which states that if you divide the concentration, the initial concentration, by the Ka value and it's less than 5%, you can assume that the change is so small that you can ignore it. So all of these questions follow the 5% rule. So what you'll see a lot of people doing is they'll write something like, so these two are equal, and they'll label it as x or something. So in this formula, you can kind of write it as x squared over b. So for these questions, you can just assume that the 5% rule is in place. So let me just write this out first. This would be x squared over this, so 0.1 minus x. And then because of the 5% rule, we can also just write this as just over 0.1. Because we're assuming that this x is so small that it pretty much doesn't matter to our calculation. Okay, so now we can plug this value in for Kb. So 2.51 times 10 to the minus 5 equals x squared over 0.1. And then solving for x, we will get 1.58 times 10 to the minus 3. And then remember that x equals OH minus. So if we have the concentration of OH minus, that means we can also find the POH, because it's just minus log of 1.58 times 10 to the minus 3, which should give you 2.8. And then our question asks for the pH. So we just need to do 14 minus 2.8, which should give us 11.2. And that's the final answer. So there we go. Most questions will pretty much follow this exact same format. Let's do another one. This is pretty much the same as the other one, but I'll do it again in case you didn't get it. So first thing, we just write down the dissociation equation. So this will be this plus Na plus. And then again, these are all equimolar, so if our concentration of this is 0.2, we can just say that this is also 0.2. And then if this hydrolyzes, remember we do plus H2O, equilibrium arrow, and then this will give us propanoic acid plus OH minus. And then again, they give us pKa, which is 4.87, and we can use that to find the Ka using not that formula. We can just do the Ka is going to be 10 to the minus 4.87, which should give you 1.35 times 10 to the minus 5. And then again, we see that we have OH here, so we need to use the Kb formula. And to find Kb, it's just the Kw of water and then this should be 7.41 times 10 to the minus 10, and that's Kb. So once again, let's set up our ice table. So CH3, CH2, COO minus, and then split it, and then the product side will be this, and then OH. And then initial, change, equilibrium. So our initial, they told us in the question, it's 0.2. And then both of these start with 0. Our change, we're going to call it x, so subtract x, plus x, plus x, 0.2 minus x, and then 0 plus x is just x, and that's our ice table. So now, just as before, we're going to use the formula. So that formula is going to be Kb equals CH3 CH2 COOH times OH minus over the conjugate over the base. And then once again, we can plug in the values. So this is going to be 7.41 times 10 to the minus 10 equals, remember that these two are equal. They're both x, so we can write it as x squared. And then over 0.2 minus x. And then we can also get rid of this x because we assume that the 5% rule is in place. If you're not sure about this, you can also just calculate the 5% rule really quickly on the side. But usually the questions will give you can just cross out x. So if we solve this, x equals 1.217 times 10 to the minus 5. And remember that this is just the concentration of OH. And then we can find the POH, which equals 4.9. And then pH is 9.1. And that's the answer to the second question.